Our next topic is the implicit function theorem. The theorem is a mouthful. It's one of those theorems that need to be understood, but it's not a complicated theorem. It just has several conditions that have to be verified, and then what the theorem says is several different things, and so we're going to look at it gradually. We're first going to see an example, then discuss what's going on, then we're going to formulate the theorem for a two-variable function, then we're going to do some examples again, and then generalize the three variables, and we'll do it step by step. Okay, so let's start with a very simple example. Very simple example. Let's look at x squared plus y squared equals 1. In the plane, in the xy plane. What is this thing? It's a circle. Do you agree? So this is just a circle in the xy plane. A circle in the xy plane of radius 1, centered at the origin. Does everybody agree? So drawing this is very easy. Here it is. The only hard thing is making sure that it comes out round, and it even, hey, pretty neat, huh? That wasn't bad at all. Do you agree that that's x squared plus y squared equals 1? Okay, providing this is 1 here. Okay. Now, is this a graph of a function? It's not. Of a function of one variable. It's not. Because at every x you look at this x. If this is x, you have two values of y. That's a big no-no according to the definition of a function. A function is a rule that assigns a y value to every x value, or more formally, assigns a value in the range to every value in the domain, right? A single value in the range to every value in the domain, right? So this is clearly not a function. Does everybody agree to that? Okay. Nevertheless, it's a relationship between x's and y's, right? So somehow y is related to x, but it's not a function by the definition of a function. Do you agree? Now, all the theory that we built, almost everything that we did in Calc 1 and now in Calc 2, is studying functions. Functions are the things that we know how to handle, that we know how to take derivatives of, that we know how to do integrals for. And this is, it's not a function. It's annoying, right? But it's only not a function if you try to grasp the whole thing as a function, right? But if you're willing to look locally, for example, look at this point here. Look just at this point. Do you agree that in a neighborhood of that point, it is a function, right? If you restrict your attention just to this part of the curve, just to this part of the circle here in blue, in a neighborhood of this point, this is the graph of the function, and we even know which function. This is the graph of the function y equals the root of 1 minus x squared. Do you agree? Everybody? So in a neighborhood of every point, it is the graph of a function. Same for here, right? It would just be negative the root of 1 minus x squared. Is that true for every point? Can you do this argument that take a point, look at a neighborhood, you get indeed a graph of a function? Would that argument work for every point on this circle? No. There are 2 points which are still problematic, and those are these 2 points. This is the point 1, 0, and this is the point negative 1, 0. At these 2 points, no matter how small a neighborhood you try to take, no matter how small a neighborhood you're going to try to take, the curve is not going to be the graph of a function. Do you agree? In any neighborhood, in any portion of this curve that you take, even let's zoom in on that point. So here's the axis, and I'm zooming in on the point. Here's the point. And no matter what small portion I'm going to try to look at, it's still not going to be the graph of a function. Because for every x value, there are going to be 2 y values. Do you agree? So these 2 specific points do not allow us to extract extract from the relationship between y and x an explicit function which prescribes the same relationship. That can be done at any point other than these 2 points. Do you agree? Okay. So let's write everything that we said. Y equals the root of 1 minus x squared, or y equals minus the root of 1 minus x squared, provide explicit functions, or not provide, or are explicit functions that that give the same relation between x and y, as x squared plus y squared equals 1. Do you agree? This is true near, this is true locally, near any point except 2 points, 1, 0 and -1, 0. Good? So except at these 2 points, we can translate this relationship into explicit functions. Good? So here's what the implicit function theorem is going to do in general. The implicit function theorem, I'm not writing the theorem yet, I'm just telling you. The implicit function theorem provides conditions. There are specific conditions that have to be satisfied in order for the theorem to hold, under which, so if these conditions are satisfied, we can do exactly what we did in that example, under which a relationship of the variables of the form some expression with x's and y's, some equality, and the general way of writing it is capital F of xy equals 0. So this is some expression including x's and y's which equals 0. Let's look at the example just for a second. In this expression, what was f of xy?
X squared plus y squared.
Right. So here the expression was fxy equals x squared plus y squared minus 1. And fxy equals 0 is precisely this. Do you agree? Okay? So back here, the implicit function theorem provides conditions under which a relationship of the form fxy equals 0, a general relationship, which is not necessarily an explicit function of y as a function of x or x as a function of y, under which a relationship can be rewritten as an explicit function, or not as an explicit function, sorry, as a function y equals f of x locally, at a neighborhood, in a small neighborhood of some point. Okay? Now, what is this word implicit and the word explicit? In the example, the relationship, which was x squared plus y squared equals 1, we actually found explicit formulas for the functions in various areas. It was a concrete function, y equals the square root of 1 minus x squared, right? This theorem is going to tell us that such a function exists. And even is going to tell us how to find its derivative. But it's not necessarily going to provide us, in fact, the theorem itself is not going to provide us with a formula for the function. It's not going to give us the function explicitly, but only implicitly. It's only going to tell us there is such a function without giving us a concrete formula for it. That's why it's called the implicit function theorem. Clear? So I want to do another example of when such a phenomena happens. When we have a relationship, we're going to extract a function, but we're not going to know the formula for it. We're just going to be able to say, to argue, hey, it exists, but we don't have a formula for it. Okay? And after we do that, we'll actually phrase the theorem. Okay, so here's the example. Let's look at the relationship y to the power 5 plus y to the power 3 plus y plus x equals 0. So the left-hand side is our f of xy. Okay? It's some relationship between x's and y's which equals 0. I don't know exactly what this looks like. If you think a minute, it can be somehow deciphered, but nevertheless, I can say a few things. So, first of all, can I write this? Can I write x as a function of y? That's easy, right? I just throw all the y's to the other side, and I have x equals some function of y, minus y to the 5, plus minus y to the 3, minus y, right? So in this case, it is easy, it is trivial, in fact, trivial, to write x equals some function of y. Do you agree? And it would be true for any x. There's no restriction, right? But can we write y as a function of x? What do we need to do in order to do that? Solve what, right? We have to solve an equation of degree 5, a polynomial equation of degree 5, sometimes called a quintic. Do you agree? Right? So in order to we have to solve this for y in order to write y equals some function of x. Do you agree? Okay? We don't know how to do that. I hope everybody knows how to solve quadratic equations of degree 2, and I hope that you all know that there are concrete formulas for finding solutions to equations of degree 3 and 4. Do you know that? Does anybody know the formulas? I hope not, because they're long. Like for degree 3, it's like 2 lines, and for degree 4, it's like 2 pages. Okay? But for equations of degree 5, in general, there's no solution. Okay? That's a very deep result. What do I mean by no solution? There's no formula that in terms of radicals, in terms of roots, gives you the solution to a polynomial equation of degree 5 and higher. That's a very deep result by two beginning 19th century mathematicians called Abel and Galois. Heard about them? Okay, very interesting people. They both died very young, have interesting life stories, and invented like half of mathematics in order to prove this. I'm exaggerating but just by a bit. Okay, they really invented a vast topic in mathematics, which is called group theory, and all of it was kind of part of the machinery in order to prove that equations of degree 5 don't have solutions, don't have formulas in terms of radicals for the solutions. Okay, there's no, like the quadratic formula, there's no such thing for degree 5 or higher. Okay, so the answer is not going to be easy, okay, because there's no formula. But the answer is yes, we can do it. It's just not going to be explicit, okay? So in general, there is no formula for finding roots of polynomials of degree greater than or equal to 5. That's what we need to do here, right? If we want to write y as a function of x, we need to solve it for y, right? But still we can make some arguments here. So here's the line of thought, and tell me if you agree. Okay, so this is, let's just recall these very important names. I wish I had time to tell you some stories about these people. They're very interesting stories. This dude here was a French revolutionist. He lived in times when France was in a lot of turmoil. There was the people that supported the king, and there were the people that supported Napoleon, and he was he sat in prison for a while, and he had a lot of friends of the Forum, and he was a pretty problematic person, but he was a genius mathematician. This result, I think, he proved at the age of 16 or something like that, and when he was about 20, he got in a dispute with somebody, probably over a girl, and at that time, if you got in a dispute with somebody, no matter for what reason, what you did is go out and have a duel. So they had a duel, and he knew that he was just, a mathematician. He knew that he was going to lose. So he sat up all night and wrote all the remaining of his ideas, wrote them to his friend mathematicians, and then he wrote letters to all his friend revolutionaries to say goodbye. And then in the morning came the duel, and he died. And he was 20 or 21, I don't remember. A very sad story, and he really introduced really pushed forward the topic of group theory, and it's an entire course that you need to take in I don't know, third year mathematics to understand Galois theory and how to prove this very extraordinary result. It's very interesting. Anyway, back to our topic. Can I write y as a function of x? Can I do that? So here's the answer. Fix x0. Fix some point, any x0 that you want. And define, I'm going to define a new function. F is already taken, so I'm going to call it phi. That's the Greek f. Phi of y. Phi is going to be a function of a single variable y, and it's going to be defined as follows. Y to the power 5 plus y to the power 3 plus y to the power 1 plus x0. So x0 is now fixed, so this is just a function of y. Do you agree? X is no longer a variable. I fixed a specific x0. Everybody with me? What is phi prime of y? It's just the derivative, right? Single variable. So phi prime of y is 5y to the 4th plus 3y squared plus 1. Do you agree? And do you agree that phi prime of y is always strictly positive for any y? Because whatever y you take, you're raising it to even powers, so it's non-negative, and you're adding 1. So this is strictly positive. Do you agree? What does it mean when a derivative is strictly positive? What does it tell you about the function itself? It's strictly increasing, right? So phi of y is increasing. Strictly increasing. Let's add strictly increasing. For every y. This is defined for every y. Do you agree? Does everybody agree? Okay. Now, phi of y is a polynomial of degree 5. You probably learned in Calculus 1 that any odd degree polynomial has a real root, right? Because it goes to minus infinity when x tends to minus infinity, and it goes to infinity when x tends to infinity, and it's continuous, right? It's going to cross that axis. Do you agree? So it has a root. How many roots can it have? It can have 5, but it's strictly increasing. Only 1. If it were to have more than 1 root, it would have to, but then it's no longer increasing, right? So as a polynomial of degree 5, it has at least 1 root. As a polynomial of degree 5, it has at most 5 roots. But as an increasing function, it has at most 1 root. Do you agree? So we can conclude that phi of y has exactly 1 root. Do you agree? Let's call that root, call it, there's only one, I can give it a name. I'm going to call it y0. Good? Everybody with me? Look what happened here. Something very odd happened here. I fixed an x0, and I found a y0. I found a y0, which is a root for this. Being a root for this, so when you take that x0 and plug it here, and take that y0 and plug it here, you get 0. Do you agree? Let's look back at our equation over here. Fix an x0. There exists a y0. I don't know what it is. I just know that it exists. There exists a y0 that you plug in here and you get 0. Do you agree? So for every x0, there is precisely one y0 which solves this. What am I saying? What am I saying? When I'm saying give me an x0, I give you a y0, exactly 1. Give an x, I give you a y. Give an x, I give... That's a function, for crying out loud. Do you agree? Give me an x, I give you a y. That's a function. But I don't have a formula for it. I just argued that it exists. Give me an x, x0. I give you a y, y0, for which y equals f of x, for which this thing is 0. Do you agree? Okay, so for every x, x0 was a specific one, but take any x, you can do it. We have a y such that that relationship holds, right? Such that the given relation, y to the fifth, etc., is 0. For every x, we have a y, and not just a y. For every x, we have a unique y. That's important. That's precisely the idea of a function. For every x, you have a unique y, right? You can't have 2 of them. Remember that? That was the issue with the circle. So for every x, we have a unique y such that the given relation is 0. So saying for every x we have a unique y, we found a function. y equals f of x. For every x, there's a unique y that satisfies the relation. That's precisely saying that we can replace the relation with a function. But this word found here is, well, not completely satisfactory because we don't have a formula for it. We just know it exists. Clear? But f is implicit. It's not an explicit function. We don't have a formula for it, but it exists. The answer to the question, can we write y equals f of x? Yes, we can, but not explicitly. Clear? This is the idea. This is the whole idea of this topic of the implicit function theorem. And in fact, the idea here in this example really exhibits the idea of the proof of the theorem, which I'm not sure if we're going to do it in full detail, but this is the idea. Okay, this is precisely the idea. Arguing from more general, here it happened because of polynomials of degree 4 being non-negative, and here it happened for very specific reasons, but in general, there are going to be general arguments that do exactly the same thing, and that's how they prove the theorem. Okay? Okay. So let's end this clip by writing the actual theorem. And as I told you, it's a mouthful, so we're going to have to discuss it a bit more, but let's just write it for now. And see that in fact it does what we expect it to do. It's going to do a bit more. I mentioned already that it does a bit more. Okay, so here's the theorem. Let fxy, this is the relation, be, or let fxy be C1. These are our standing assumptions throughout all the theorems in this course. In a neighborhood of a specific point x0, y0. So remember what C1 means? Continuous partial derivatives, right? Such that, so this is already an assumption. We already have to check it before we apply the theorem. Okay? Such that, and there are two more assumptions. One, f at the point itself is 0. So the point which we're looking at satisfies the relation. Okay? So for example, let's take, so every time I write something, I want to exhibit it on the example of the circle over there. So in this example, this was our f, right? Look at this, thanks. This example, this was our f. It's clearly C1 on the entire plane, right? But the points I'm interested in are not points of the form negative 15, negative 21, right? I'm looking at points on the circle, okay? And at any point on the circle, other than problematic points, and the problematic points are going to be ruled out by the second condition that I didn't write yet, but the points have to be on the circle. Being a point on the circle means that f at the point is 0. Do you agree? Okay, so that's what x0, y0 has to be. It has to be a point on the circle, that f at the point is 0. Is that clear? So at points like this, providing they're not problematic, like this one, we're going to have the statement of the theorem. So back here, such that f at x0, y0 is 0, and this is the condition that the problematic points in the example don't satisfy. The derivative of f with respect to y at the point is not 0. Good? Let's look again at the example. Back to this board. In the example, what's the derivative of f with respect to y? It's 2y. At which points is the derivative of x with respect to y, 2y, equals 0? Precisely at these 2 points. These are precisely the points to which the theorem won't apply, because they don't satisfy condition 2, that the partial derivative with respect to y cannot vanish. Clear? Okay, so these are the 2 conditions. If these conditions hold, then there exists a neighborhood of x0, y0 in which we can write y equals f of x rather than f of xy equals 0, such that, so what do I mean we can write y equals f of x? We're not going to have a formula for it, so maybe let's not write we can write, in which there exists a neighborhood in which there is an implicit function y equals f of x, such that let's call it little 1, little f of x0 is y0. So the point itself satisfies it, x0, y0. 2, if we take our relation f of xy equals 0 and substitute the y's by f of x, that's saying writing y as a function of x, then we're going to get 0. So y equals f of x is indeed an implicit function expression of this relation. Okay? For every x in the neighborhood, and the third condition, this we haven't discussed yet in our examples. We only discussed about the existence of y as a function of x, implicitly or explicitly. But the third part is also very useful. There is a formula for calculating the derivative of f, although we don't have a formula for f, but we know how to calculate its derivative. And the way to calculate the derivative is minus, take the partial derivative of f with respect to x and divided by the partial derivative of f with respect to y. And remember that the denominator here is not 0. That was this assumption here. Okay? So, okay. And this is again in the neighborhood, Clear? Okay. So this is the theorem. What I want to do, but that's going to be in the following discussions. What I want to do is take a concrete function. Maybe we'll phrase this for 3 variables just so you see how it extends. It's very similar. You just have to replace f of xy with f of xyz. And then x0, y0 is going to be replaced by x0, y0, z0. And then this assumption is going to hold for one of the variables, and we're going to be able to write any of the other variables as a function of the other two. So y is going to be f of x and z, for example. And so we'll rephrase this again just to get used to it. You understand why I said that it's a mouthful, right? It's kind of a big theorem. And then we'll do examples. We'll take a concrete example, a relation for which we can't just extract y as a function of x, and we'll use the theorem to do so. Okay? So all of that coming up next.